Salutations, my fellow colleagues. This is 191, number of 1 bits. This one's not too bad, but it might be tough to get a faster solution if you don't know about a few tricks you can use, but we're going to go through that real quick. So it says, write a function that takes an unsigned integer and returns a number of 1 bits it has, also known as the Hamming weight. Then this is just some extra notes about binary representation, 1's complement, 2's complement step. Follow up, if the function is called many times, how would you optimize it? And this is a hint at better solutions, right? So input n, you have a ton of leading bits here, or assume that the maximum number of bits here is 32. But I think that's what they're assuming here because that seems to be what is here. And you have 1, 0, 1, 1 at the end. So basically this number is, if you know your binary number is a little bit better, this is going to be 1, 2, 4, 8. So this is 8 plus 2 plus 1, so this is 11, right? And you have to return the number of 1s in this string, basically. Well, not a string, but this number. And so the output here is 3. But what you're given is not, a binary string. What you're given is an n, which is an integer. Now, what you can do, which is not a bad way to solve the problem if you have to solve it on the fly, what you can do is you can just do, let's just say you're given the number 8, right? We convert that to binary, and what you get is, let me switch back. So you have the number 8, and you convert that to binary. What you'll get is 1, 0. I mean, not the number 8. If you have the number 11, which is what they gave us, you convert that to binary. What you get is 1, 0, 1, 1. 1 here representing 1, 1, 1. 1 here representing 1, 2, and 1 here representing 1, 8. So basically, this comes out to 8 plus 0 plus 2 plus 1. So you have 1, 1, 1, 2, and 1, 8. You get 11, which comes all the way around to equal 11, right? So what you can do is you can convert this to binary, right, which is a linear operation. When done with whatever language you're using, it's going to be a linear operation. And then you'll get 1, 0, 1, 1 back, right? And then this is just a string now, right? You can just iterate through the string. Oh, we found a 1. We'll increment our counter, which will be, let's just call it total. Let's just call it total. And then you'll go through, you'll be like, oh, we got a 1, 0, 1, 1, total equals 3, right? So everything works out there, right? But we can actually do better than that. So we can get an answer in a logarithmic time. And that is going to be much, much, much faster. So how would you do that, right? So there's a concept, right? When you have it's a method that's used to convert base 10 numbers into decimal numbers. And some of you might remember this from school, but let's just say you have the number 15, right? And you want to convert it to binary, right? How do you convert this number to binary, right? So there's an easy way you can actually do this. So what this method is called consecutive divisions by 0. And so what you can do is, I'm just going to walk through this with you guys. And what you can do is I'll just write the answer here, and we'll kind of fill it in. But let's just start with 15. So this is how you do consecutive divisions by 2. So we have 15. We're going to divide 15 by 2. 2 goes into 15, right? 7 times. Really 7.5 times, but we're going to add the remainder here now. So 2 goes into 15 twice. Our remainder is going to be 1, right? Because 2 times 7 is 14, right? And our remainder is 1. So now we have 7. 7 divided by 2 is equal to 3.5, but we're just going to put 3 here because the half is going to be represented by the remainder, right? Because 2 goes into 7 3 times, and you get 1 left over, so you get 0.5. But 1 is half of 2, so our remainder here is going to be 1. Then you have 3 divided by 2. It goes into 3 once. Our remainder here is still 1, right? And then we have 1, right, divided by 2. I think I've just been using the mod operator the whole time. I meant divided, not the percent sign, which I've been using the whole time. But So yeah, we're going to be the 1 divided by 2 is going to be equal to 0 because 2 doesn't go into 1 at all, right? And our remainder is 1, right? And you can go up this way and you'll get the binary representation of this number, right? So let's just do one more just to see how that could be done differently with the right symbols. So we have 12. We want to represent it as binary, right? How do we do that? We start with 12, just like we did before, divided by 2. You get 6, remainder 0, right? Okay, we have 6, I keep using mod by mistake, divide by 2, and you get 3, remainder 0. Now we have 3 divided by 2, we get 1, remainder 1. And we have 1 divided by 2 goes into 1 0 times. Our remainder here is going to be 1. And then if you go up this way, what you get is 1 1 0 0, which evaluates perfectly to 12, because if you know your binary places, boom, 8 plus 4 is 12. We have no 2's or 1's, so this is equal to 12, right? So let's go back to the code here now that we see how this works. If we go back to LeetCode, what we can see, right? So we'll look at the question one more time, right? So we have to write a function that takes an integer and returns the number of 1 bits it has, right? And we can see that in our drawing, I mean, we're getting both of those outputs, right? We're getting every single digit or every single binary digit in its binary representation. So you're getting the 0s and you're getting the 1s here, right? So now it becomes pretty remedial to just be like, is our remainder 1 or is it 0? We'll just count all the times that our remainder is 1. So let's do that. So this is what we're going to do. We're going to say total is going to be equal to 0, right? Because this is just going to be what we're returning. Total 0s. And we're just going to return it here, right? And then, right, when we were dividing, right, every time we were dividing, when did we stop? Oops, I didn't go back to LeetCode. So just to reiterate, we're going to put total here is going to be equal to 0 because that's what we're returning, and then we're just going to return it here. We're going to write the code in the center. So when we were drawing, when we were doing our division, right, when did we stop, right? We stopped when did we stop dividing, right? We stopped dividing once our answer, or what returns from the division, is 0, right? And so that's what we can do here. So we'll go back to LeetCode, and we're just going to have a while loop. We're just going to say while n does not equal 0, right? And then what we're going to do is, how did we have to count the number of 1s or 0s that, well, the question says we have to count the number of 1s, right? So how do we do that, right? If we go back to the drawing and iterate in the drawing here big time, we saw that when we do 12 divided by 2, we get our answer, which is 6, and then the remainder is actually, the remainders in reverse is actually what you get as the binary representation, right? So we need to get the remainder of this division, right? And what can we use to get the remainder? We can use mod. And so mod is basically division, but you only get the remainder back. So we'll say if n mod 2 is equal to 1, then we're just going to add 1 to total, right? It means that for whatever denomination of the number in the midst of the division we're at, if we got 1 as a remainder, we're going to have 1 in the binary representation. And that's what we want, right? But this is a while loop, right? We don't want this to go on forever, and we don't want to just keep modding by 2 over and over again, right? So if we ran this with 12 as our input, while 12 does not equal 0, okay, we're going to go inside. 12 mod 2 is going to be 6, so we're not going to add anything there, right? And this will just run forever, right? So how do we keep this going? So just like in the, so we have if n mod 2 is going to be equal to 1, total plus equal 1, right? But we need this to keep going, right? So how do we keep it going? If we take a look back at our drawing, I mean, what's integral to this process here is division, right? So we're getting the remainder with mod. Now we need to actually divide, right? And so this is kind of where the magic happens. N is going to be equal to the integer representation of n divided by 2. And if we run this, we'll see that we get the answer, and it's a lot faster than most solutions, right? It's because it's going to take, log of n time. I'm going to explain why that is. But if we go back to our, well, we don't have to go back, but if you take a look here, if we do n divided by 2, like we said when we were dividing 7 divided by 2, you get 3.5, right? But we want to work on the bottom end of that spectrum, right? We just want the whole number version of that, right? So once we get to, let's just say something like 1 divided by 2, right, you're going to get 0.5. Well, that means nothing to us, right? What we want is to truncate that value, right? And so what we'll get is 0, right, because we're going to go downwards. So if you have 7.5, right, and you cast it to an integer, what you're going to get is the value going downwards there, right? So the floor of that value. And so this is why we're putting this in here. Because otherwise, our case would have to be while n is greater than 0.5. And I think we can see that if we do this here. Yeah, it's a little bit more complicated. While n is greater than and over 2, yeah. So this is why we're going to be doing it this way. Oops, I have to change one more thing. While n does not equal 0. That's my bad. So it's going to run for a while before it says time limit exceeded. But why is this? Why is the time complexity here log of n, right? And it's log of n because if you take a look, we're going to look at the logarithm calculator here. What we're doing is we're taking a number, right? We're doing consecutive divisions by some amount, right? So how many times are you going to do that division, right? And so it turns out the log base 2 of the number we receive, we're going to get the number of divisions that we need, right? So we did 16 earlier, and we saw that it took us 4 divisions to get to the answer of converting the number to its binary representation, right? And this is going to scale perfectly. So let's see. If we do, let's just say we do a ton, right? We'll find that it only takes us 23 operations to count the number of ones in this, right? Which is pretty good. So this solution is going to be a little bit better rather than casting this, converting this to a string and then linearly iterating over to count the values, because the linear iteration might be more steady when you have, always going to have 32 bits, right? And so on and so forth. But this is going to be better when you have different numbers ranging from, different numbers represented with different amounts of bits. This is going to